Hello, in this tutorial we'll talk very briefly about Zen's quantum capabilities. Some of this won't be understandable unless you've read a primer on quantum computing and quantum computer music. This is not the place for that here, but if you look in the documentation under Zen Quantum, there are links to the quantum circuit library developed by Quantastica, which is the engine that's powering Zen Quantum, as well as some interesting papers by Miranda 2022, which explains quantum computer music in more detail. So in Zen we can build quantum circuits, and we can use the data that comes from those quantum circuits as values within our musical algorithms. So first, how to build circuits. So Zen uses another class, we'll introduce another class, which is the qubits class. Qubits are quantum bits. They're the smallest component of information in a quantum computer. So they're the parallel of a classical bit. Qubits are a class in Zen, and they are represented by Q for qubit, and then an index. So you can have Q0, Q1, Q2, Q3, etc. And all of these are represented by a wire in your quantum circuit. So we can chain gates. So I can apply a Hadamard gate, and we see that the Hadamard gate gets placed on the wire. So just as in classical computing, you can apply logic gates to classical bits, and that will change their state. In the same way, gates can be applied to quantum bits, and it will change their states. A Hadamard gate puts a qubit in a state of balanced superpositions. There's a 50-50 chance that when that qubit is measured, it will return 1 or 0. So if we have a look over here, there's a roughly equal distribution of 1s and 0s when we measure this qubit. Next, let's put a CX gate, and we'll link it with qubit 1. And this is a conditional gate. Each time this qubit is 1, then an X gate will get applied to this next qubit, which will flip its state. So we can see, as a result, that when qubit 0 is 1, qubit 1 is also 1. They're linked. We can flip that by doing this, qubit 1.x, and then we get opposites. We get a 0, 1 when qubit 0 is 0, and 0 when qubit 0 is 1. So for a full list of gates, have a look in the documentation. I'll point you to that at the end of the tutorial. But let's have a look at what it means then to use, what kind of data can we get from this circuit, and how might we use it within our musical algorithm. So let's just set up our trusty synth, and so if you remember, our E parameter stands for events, and it expects a pattern that when it's 1, it will trigger an event, when it's 0, it will be ignored. So any pattern method that's to do with the quantum circuit begins with a Q. So we can do Q measurement, and we can say which qubit we want to measure. So I'm going to say, let's measure qubit 0, and each time it's 1, trigger an event, and each time it's 0, ignore it. So we can see, let's do a cut. We can see the correlation between the measurement of the qubit and the triggered sound. We can also do quantum measurements, which returns an array of all of the qubits, and we can do something like @0, and we get the equivalent. But let's have a look at print this point, you can see we get an array of all of the qubits. It can be tedious to write something this long out, so QM is an alias for quantum measurement, singular, and QMS is an alias for quantum measurements, where we get the array of all the measurements. Okay, so anywhere that you want ones and zeros, you can use the measurements of all the qubits or a single qubit as data within your musical algorithm. Let's have a look at probability now. So let's just set this to every 2. So let's talk about basis states. So in a circuit like this, it's a quantum system consisting of 2 quantum bits, 2 qubits, and there are 4 possible outcomes from this circuit. It could be 0, 0, 0, 1, 1, 0, or 1, 1. So there is a probability amplitude for each of those basis states to say how possible it is that when measured, that will be the basis state that is arrived at. So if we do S0, and let's just make up a completely random parameter that's nothing to do with the synth, and let's do Q probability, and let's say what is the probability of the first basis state 0, 0 being true. Now if we print that, we'll find that there is no chance that 0, 0 will ever happen, and that's because the way we set up the circuit means that these are always in opposition to each other. So then what is the probability that the next basis state 0, 1 is possible? And we'll see it's a 50-50 chance. What is the possibility of the basis state 2 being true on measurement? Well, that basis state is 1, 0. So again, there's a 50-50 chance that that's true. And what about basis state 3, which is 1, 1? It's impossible because we've set these up in opposition to each other. You can also do probabilities, which gives you an array of all the different probabilities. And if we were to remove this, for example, we'll see that this changes at the bottom, because rather than them being in opposition to each other, they're always the same. Okay, here is the phase. So the phase is to do with the rotation around the z-axis for each basis state. So as we're not doing anything with z rotation, we're not going to get any interesting results, but let's have a little look at Q phase. Let's do Q phases right from the off. And the phase component for each basis state is 0.5. Now let's actually do some rotations around the z-axis. We can start to see that as we rotate qubit 1 around the z-axis, we start to get different values. Now's a good time to say that the arguments that you can pass to a gate can be raw values, or they can in fact be patterns. And remember, if you want to spawn a new pattern, you've got to prefix it with $1. So we can start to see that we get some more interesting values happening here. And if we were to add an RZ gate here as well, let's do something like so. We get some more interesting outcomes. So again, you can use the phase value of each basis state as other data to be used within your musical algorithm. Q phases, I think, can be written like this. Oh no. Q probabilities, I think, has an alias QPBS. That's right. result. So this is the actual measured outcome of the circuit, which basis state it turned out to be. So if I do cube result and we'll print the outcome, at the moment it's a rough equal distribution between 0 and 3, which means that, again, there's a 50-50 chance of the state being, the measured outcome being 0, 0 or 1, 1. If we are to apply the X gate here again, that should change to between 1 and 2. Because here we're saying that only 0, 1 and 1, 0 are basis states that will be returned. So just to recap, you use the qubit class, which are represented by Q0, Q1, etc. In order to build up your circuit, and you can use to place different gates on each wire. And then when we come to use the data that we can get out of the circuits, we've got access to the measured outcome of each qubit, the probability of each basis state, the phase component of each basis state, and the actual result of all the measured qubits. All of these are available as pattern methods or prefixed by a Q. In the docs, as pointed to before, the quantum Zen quantum tutorial page has more detailed explanation of how to place gates and how to take measurements and apply them to musical algorithms, including some source code ideas to get you started. But also, if you're wanting to have a look at some more complex usage of quantum algorithms, phd.cephastium.co.uk has some compositions that are very focused on sonifying quantum algorithms, and there's links to videos of live coding performances as well as studio recordings, and links to GitHub repos showing source code where we build more complex circuits and we sonify them, so they might help illuminate this subject a little more. Thank you.